First, I'll say that I wasn't expecting to do this. Harish was supposed to be here. So we had three of us sort of leading the discussion. And I don't have the slides from the three. It was Pete Moosbrugger from Ball. So he's in charge of developing their phased array, the 28 gigahertz new commercial sort of prototype that people can use to investigate development of 5G systems. And so he discussed the advantages, and this isn't on the notes here, this is just sort of the preview. Pete discussed the advantages and disadvantages of various phased array implementations, fully digital, hybrid, and more traditional sorts of phased array. And he really made the point that the business case needs to drive the decisions on what technologies to use. So and then that the decision on which type of phased array implementation to use may change as technology advances. So for example, people are using hybrid arrays right now. That makes the most sense from a business case point of view, but there may be a time in the future where the fully digital implementation of the phased array starts to make more sense. Harish, he's professor at Columbia, and then he also has a startup called Mixcom, where they're doing RFIC design. He touched on several different open challenges regarding which technology to use for 5G implementations, silicon or 3.5 based or hybrid types of technologies are all candidates right now. He also talked about which architectures to use to improve system efficiency. So the fact that the amplifiers are, need to be operated in very linear operating states right now means the efficiency is very low. That will also probably change in the future, but there are certainly technology or architectures that can improve system efficiency, technologies that can improve system efficiency. And so the choices that are made now are sort of the most safe to get systems up and out the door, but things are likely to improve over the course of the next few years, and we discussed that yesterday here also in the panel. And then, being from NIST, I discussed the role of measurement in improving models and reducing the need for digital signal processing, things like digital pre-distortion. So I gave a couple of examples on the use of measurement uncertainty to improve the nonlinear models that are being developed for transistor design, showing that if we extract model parameters from large signal measurements, that by doing sensitivity analysis of the various extracted parameters can lead a designer to understand what the weak points are in the transistor model development. So for example, if you run something near compression or high current, you can see very clearly from the uncertainty or error bars that there are weaknesses in certain parts of the waveform as you're nearing compression. I also gave some examples on the use of channel measurements for directional array design. Based on our NIST channel sounder, we can synthesize an omnidirectional radiation pattern. We have a switched array that samples very quickly in the azimuthal plane. From that, we can synthesize an omnidirectional array, and then we can actually take the measured data and start synthesizing narrower and narrower beam widths, so that a designer, an antenna designer, could see the effect of various beam widths, based on measurements in a specific environment. And then also talked about over-the-air measurements and how those can be used to verify the performance of devices and then to improve the performance of devices. So that's a big issue right now in the 3GPP is the OTA test of the millimeter wave devices, because they need to be verified. The performance needs to be verified in sort of these 3D spatial channel models. And so I showed an example of a hybrid chamber that NIST has developed to create specific 3D spatial channel models, essentially in physical space, based on a reverberation chamber that's very heavily loaded with RF absorber on the wall, so essentially like an anechoic chamber, but then certain patches are left reflective to create the angular clusters of multipath that are specified in various channel models. And then the sort of key value added that NIST brings to this is the verification of these environments with the synthetic aperture techniques. So that was sort of the introductory comments that the three of us made. And then we had a very nice discussion, focused a lot on the beamforming arrays, which is not really my expertise, but was certainly the expertise of a lot of folks in the audience. And so the first question that we tackled, will fully digital arrays ever become a reality at millimeter wave frequencies? And as I mentioned, well, there's a lot of advantages to fully digital, so people are trying to head that way. The hybrid array is not as efficient in shaping the beam, but the hybrid array, I think this is the big advantage right now, only uses a few ADCs, and then of course, one RF or fewer RF chains as well. So, eventually, I guess right now, and Ted touched on this also, if the millimeter wave use case is primarily line of sight and maybe has 3 or 4 clusters, does it really make sense to use a fully digital array, or are we fine with just a hybrid array having 4 or 8, various beams that it can create? So that's sort of a fundamental question. Fully digital is quicker when it's used for the initial access, the discovery of the channel. So, ultimately there are probably advantages to using that. It may be, this is something Pete brought up, a fully digital system would likely be more difficult and complex to maintain in the long run, just because you have more of these moving parts, the active parts, the antennas, or sorry, the RF chains and the ADCs. Let's see, and then there was a discussion on this concept of open loop beamforming, where you don't monitor channel conditions in real time. You just assume that the coupling between the elements is constant and that you have adequately tuned your array for, to minimize blind spots. Closed loop beamforming, you can compensate for non-idealities like coupling and unexpected scattering in real time, but at the expense of power. So power is a big issue for the millimeter wave systems and the system complexity in terms of the long-term, maintenance and usability of the system. So it was argued that open loop is generally satisfactory, and if a few elements are operating in a nonlinear state, like because of coupling, signal conditions, or something like this, it won't be all of them, and so and that tracking and blind spots don't change that rapidly in practice, so that gets to this idea of the coherence time of the channel, and that we're really mainly tracking 3 or 4 clusters at a time. So let's see, for now the cost of a fully digital array might be high and the reliability might be low, but that's today. So the potential is very high for using fully digital arrays if lower cost ADCs could be produced as technology advances. And so there was a lot of confidence in the room, I would say, that fully digital will be a reality at some point. I mean, everyone pointed out that right now in the sub-6 region, we have fully digital arrays, and 10 years ago, you never would have thought that could be possible. So one of the questions that Harish brought up is, but is 5G a large enough business or commercial entity to drive the development of these low-cost ADCs? And so perhaps other applications might drive the development. For example, if Internet of Things really takes off, and the industrial environment, or these other very high reliability use cases like automotive applications, perhaps the millions and millions of nodes that would be a more likely driver for the development of fully digital arrays. Let's see. If the applications are primarily line of sight, why use beamforming at all? These are questions that came from the audience. Why not use mechanical systems? And the answer there is that right now, it's performance versus cost. So operators do not want this first generation of 5G to fail. Phased arrays are proven. We know that they can work in this hybrid technology. They're cost effective. So that's what is going to be used right now. Let's see. acquiring channel state information. Is there a high overhead for training fully digital arrays? In mobile multi-user applications, fully digital is more powerful, and I think Sandeep had a paper to demonstrate that. To make digital arrays more cost-effective, you could reduce ADC resolution. Okay. All right, on to question 2, augmented virtual reality. And this was just interesting. It was estimated that each user would need 3 gigabits per second of data with a latency of 10 milliseconds or less. So can 5G do this? Well, the panel sort of said, well, maybe 6G. That really is beyond the capabilities of even current, in the near future projected technology. Question 3 on PAs, power amplifiers, and digital pre-distortion. For example, if you had 256 power amplifiers in your array, and not all of them compress at the same time, how would you apply digital pre-distortion? Can you use an average over the entire array? Well, you could actually apply digital pre-distortion on each data stream. So again, if you had a hybrid array, you would be applying the pre-distortion on each of those subarrays individually. So that's maybe not a showstopper. There was also some interesting comments on third-order intermodulation products. If each power amplifier in an array creates its own intermodulation distortion, and the IM3 has a different phase from that of the main beam, it essentially creates its own distortion beam in some undesired, maybe not random, but undesired direction. So various research groups, and I thought this was really interesting, are using shaping techniques to direct the distortion products, so the beams that are caused by the third-order intermodulation distortion away from the desired directions. You could also direct, and then Harish brought up the point that, well, maybe using these techniques, you could actually direct IM3 away from a receiver in the presence of a blocker to overcome some interference issues. So these are just ideas that came out of the group. And then the final question was, the new radio bands are very reconfigurable. LTE always had a fixed, you designed your system to operate at a fixed 20 megahertz bandwidth, whether you use the whole 20 megahertz or not. That was the system that you designed. So what are some of the issues in hardware circuit design for systems that are very reconfigurable? And this answer is very abbreviated, but the bottom line here is that reconfiguring hardware, so components like filters, and then the ADCs with the sampling rates, it's difficult, but that there is quite a bit of research in the area. So that's what we had.
Well, one thing I was wondering, so in terms of the interface signal processing, it seems like pre-distortion techniques, clearly signal processing has a role to play in terms of the subarrays. And then in the filters, some of this, why do we have to have hardware reconfigurable filters? You could do it in software too, that you're only using sending signals on a partial stream. It won't be as, the leakage won't be as controlled. So I don't know if it's necessary or not.
I think that the trade-offs are the power consumption and the complexity that's required to implement things in signal processing, or DSP versus hardware itself. And we actually talked about, some groups are trying to get away from the use of digital pre-distortion and go back to sort of the old techniques of using analog circuit design to compensate for distortion. This idea of coming up with better designs, maybe using lookup tables more as opposed to real-time analysis. Any little tricks that companies can use to minimize power consumption, they're really trying to do that right now. And so I think hardware implementations are actually are less power hungry typically.
Power hungry, yes. Yeah, I think that's a good point. Okay, that's one of the reasons why hybrid beamforming is being used as well.